You hike out to the perfect spot, set up your portable solar panels in direct sunlight, and then wait. The charging is slow, and the battery packs and inverters you hauled out there are heavy and run alarmingly hot. The bottleneck preventing you from pulling fast, usable energy isn't the solar panels capturing the light. It's the hardware gating and converting that direct current into a format your devices can use. For decades, that power conversion has relied on silicon, the material that established the historical legacy of Moore's Law and built our modern electronic ecosystem. While silicon defined the early digital age, it has reached its absolute physical limits. That ceiling is the reason off-grid gear is still too bulky to carry comfortably. When silicon is forced to manage high power levels, it acts like a stiff valve, leaking massive amounts of energy as waste heat. To keep that tiny chip from melting, engineers have to surround it with massive copper inductors, large capacitors, and heavy metal heat sinks. These thermal management components add the vast majority of the dead weight to modern solar backpacks. If you replace that core semiconductor with a material that runs faster and cooler, those giant passive components are no longer necessary. Solving that microscopic heat problem improves chip performance and dictates the physical volume of the entire solar setup. Gallium nitride, or GaN, is an advanced material already trusted in satellites and military radar, and it is now coming to consumer solar hardware. The core difference between GaN and silicon is the band gap, a measure of the energy required to make a material conduct. Silicon has a narrow 1.1 electron volt band gap, while GaN's is triple that at 3.4. Pushing energy through the narrow silicon channel creates significant friction, which is lost as heat. GaN's wide band gap allows it to open and close its electrical valve instantly, allowing current to flow with almost zero wasted energy. This wider band gap eliminates the microscopic friction that causes devices to overheat, enabling a significant leap in electrical efficiency. This graph comparing power output to switching frequency shows GaN's primary advantage. It can operate at up to 400 kHz. This allows the system to switch power on and off at frequencies far beyond the absolute theoretical limits of silicon. Because GaN switches so fast, the system no longer needs to store and smooth out large amounts of energy at once. You can watch the physical result of that speed here. The bulky metallic coils and capacitors rapidly collapse into a tiny compact circuit board. This unlocks 97% power efficiency in hardware that is 4 times smaller and 4 times lighter than silicon equivalents. In power electronics, switching speed determines system size. Faster microscopic switching enables physically smaller macroscopic hardware. By 2026, bulky 10-pound inverters will be replaced by consumer modules that fit in the palm of a hand. This chart compares energy extraction in overcast conditions, highlighting a significant performance gap between the two materials. While silicon inverters struggle to extract usable power when the sun isn't at peak intensity, GaN maintains an efficient energy capture curve even in low light. GaN lightens the physical weight of the pack and maintains the reliability of the power source, even when the weather turns. These gains come with manufacturing hurdles. GaN is difficult to produce, requiring expensive substrates like sapphire to grow the crystalline films. The material is electrically sensitive. As this oscilloscope shows, if the gate voltage is not perfectly regulated and exceeds just 6 volts, the chip will fail. This sensitivity means engineers cannot simply swap silicon out. They must design specialized drivers to handle GaN safely. However, these engineering challenges are solvable, whereas we have reached a permanent physical dead end with silicon. Mastering gallium nitride allows engineers to bypass the thermal limits of silicon, delivering portable power as light and fast as the industry originally promised.